tell you how to calculate the pressure, so let me talk about it. How would you calculate the pressure? There are balls in a room hitting the wall. How would you calculate the pressure? Yes?
Measure the change of momentum due to balls hitting the walls.
So let's talk about it. Very good. So what you are saying is when the ball comes in and gets bounced back, it imparts some of the momentum into the wall, right? And what is pressure? Pressure is force divided by area, right? So what it has to do with momentum?
dP over P times A equals dP over dt.
P times A is equal to pressure times the area is equal to what?
dP over dt.
Change in momentum per unit time, right? So we can assume that this happens in dt time. So basically your pressure is proportional to, with all the other things, it's proportional to change in momentum, which is proportional to change in velocity, right? In x direction. So what we are talking about is that you come in with Vx, you go out with minus Vx. So the pressure in this case is proportional to 2Vx, or just proportional to Vx, right? How we treat the area? Well, it's a two-dimensional system. So we can assume that there is some depth to this system, and the area is proportional to the length. So we should divide by the length of the wall. Okay, that's pretty much it. And we can look at the code that we had before. Okay. I've changed the codes a lot. Was this the last code that we did? I think it was the last one. So let me see where we are dealing with pressure. Do you see this point? So there is a collision with the left wall. So the way that we did it is we had a box and we were moving the right wall, right? So I was calculating the pressure on the left wall, which is not moving and also which is not increasing its length. So the pressure is supposed to be the same everywhere. That's why I'm only using this side. Of course, okay, very good. So what do? 2 times the velocity in the x direction divided by the length of the wall in y direction. Okay, and what do? At the end, we summed all the momenta imparted on the wall. This sum could be also the mean. We could also look at all the walls or whatever. Remember that none of these things that we have calculated is true to the, it's all qualitative numbers, not quantitative. You can't go out and do the same experiment and get the same pressure. There's always a coefficient in front of it, okay? What else we did? So I did some changes. Do you remember how we were calculating entropy? I did some changes. Would you like to hear them?
Please.
Thank you. So I go to my private codes. One moment. Yeah, I've tried many things. You will see them here. You see, there are nicer pictures now. Do you like them? And a bunch of experiments. So I want you to this is my favorite one, actually. Do you notice something about the temperature?
It's fluctuating.
It's fluctuating. It wasn't fluctuating before. And I was bothered by it, if you remember, right? Then I remembered what temperature was. Let me tell you, let me ask you. Let's say you have, so let's talk about temperature as well. Temperature. Can you define temperature? Can you tell me, let's say it's high school definition? The total vibrational energy, that's very important. Or the total energy due to random motion of particles, objects, atoms. So the slight difference there is that, here it is, like I have a ball that is 300 Kelvin, okay, so jiggling around. If I throw this ball with some velocity, like let's call it huge velocity, 100 meters per second, huge, right? Will the temperature change? It's in outer space. There's no friction, nothing in front of it. Just 300 Kelvin ball, I'm throwing it with a very high velocity. Will its temperature change? Do you understand my question? There is no friction. There is no friction. So it will not change. Here's the thing. All this energy due to this ball moving with 100 meters per second is mechanical energy. Okay? So if we were to look at their velocities and trying to get temperature out of their velocities, there will be always this extra 100 on the average. So how do we get the temperature? We first subtract the mean of the velocities. I hope you are following. Then we do the mv squared over 2 sum. You don't buy it?
I didn't understand.
You didn't understand it. No worries. So what is happening here? Before it was moving with 100 meters per second, they were jiggling, right? And that jiggling is also huge velocity, that jiggling. But once they start moving with, like, add 100 meters per second to each one of those jigglings, then if you do sum of mv squared over 2's and make it temperature, it's wrong. Okay? We should write v minus v center of mass squared. That's what I'm trying to say. So that's what I'm doing now in this new programs.
I have a question.
Sure.
What if I have two balls and throw them like that?
Yes?
In this case, their center of mass velocity will stay the same. Since the half of the particles got velocity this side and other half got velocity this side, but their mean kinetic energy will increase.
Brilliant. That's right. Very, very nice. So, first of all, in this case, still the temperature of both balls are 300 Kelvin.
Yeah.
Absolutely. Not related to our calculation. But if we were to do that calculation in our computer, we would be wrong. Because it's a special case. You have created a special case where the velocities once we remove the center of mass velocities, what remains is not random velocities. Okay, so by definition, temperature is defined as energy due to random motion of atoms. So it won't obey to that definition. If you accept that answer, would you accept that answer? It's no longer a random. First of all, the system is no longer in thermal equilibrium, because in thermal equilibrium you expect Maxwell-Boltzmann distribution, but you will have two peaks that doesn't obey Maxwell-Boltzmann distribution, right? But very good point. Yes. Sum of kinetic energies divided by, yes, average kinetic energies, times something depending on the degrees of freedom, right? 3/2 if it's, so the average of kinetic energy will be 3/2 kBT if it's 3 dimensions. It will be just kBT if it's 2 dimensions. Do you remember that part? No. So let me just put proportionality here so that you don't bother yourself with what is in front of it, coefficients. Are we good? Yes? So let me show you where I have implemented that. Here it is. I first find the velocities minus their mean, then I take their squares. But why it fluctuates? Wouldn't the center of mass velocity remain the same? Wouldn't the momentum be conserved? Well, it doesn't, because we assume that there are walls. Yes, exactly. We assume that the walls have infinite mass, or even if they don't, we don't take into account the momentum of the box that is moving. So every time the ball hits the wall, it actually moves the whole box a little bit, but we don't take that momentum into account. That's why the momentum inside our box is not conserved. Good? What else did I change? So, for example, I tried this. Instead of moving one wall, how about moving all 4 walls together? Because that way you create volume expansion with less wall velocity, so you are bothering the system less. Okay? That's another change that I made. I will put the ultimate very nice working code in the code, and you will see it. What else? I've changed the way that I was calculating entropy just a little bit, so no need to worry. Remember, we were putting things in grids, and we were calculating where it falls in those grids, right? This time I'm just adding a Gaussian, okay, to every grid. Instead of putting just one, I'm adding a Gaussian that has the same amount of spread as the size of the boxes. Let me show you how I do that. So I calculate the Gaussians in each direction. These are the Gaussians in each direction, and then I multiply them together. I was very hopeful that this will bring some serious change. It didn't. The only main change is that I don't need to worry about zeros anymore, because wherever I put a new particle, the Gaussian's tail will spread to everywhere. Okay, so that was nice.
What were you expecting by putting Gaussians?
I was expecting less fluctuation in entropy, because I was thinking that maybe, okay, it's fluctuating too much because I put it in this box, then I move it to this box, it suddenly changes, right? But while if it's a Gaussian, it will change more smoothly. I didn't quantify it, like compare what happens when I do that or this. You can do that in the homework if you want to get bonus points. But in any case, it didn't change. I felt like it didn't change. What else?
What is mp.outer?
Oh, yes, very good point. So, since you asked, I was not going to explain it. Let's for a moment think about position x and position y, so that we don't bother ourselves with 4 dimensions, right? The way that I implement it is that what is the position? I put a Gaussian like this in x direction. What is the position in y direction? There's a Gaussian like this. The outer product is just outer product of these two, so that it creates a 2-dimensional, like this is here, this is there, so there's a Gaussian that is 2-dimensional. So I multiply these 2 vectors. But then there are not just these 2 vectors, there are 4 vectors, right? There's position x, position y, velocity x, velocity y. So it's you are supposed to do a 4-dimensional outer product. So the way that I do it is I first take the outer product of positions, then the velocities, then I put them into these matrices. So I expand 2 by 2 matrix into 4, no. I expand 10 by 10 matrix into 10 by 10 by 1 by 1 matrix and multiply it with 1 by 1 by 10 by 10 matrix. Did it make sense? So that I get 10 by 10 by 10 by 10 by 10 matrix. You got it, of course. Should I repeat it? No? Good. What else I did? The best result that I got here, this is the best result. It's also some sort of a philosophical journey, like there's an entropy. Anyways, so the way that I did it is that I expand the system. Let's say it takes some time. Then I wait the same amount of time in this state so that it just calms down. Does it make sense? Then I keep expanding so that it goes this way. Then I stay the same amount of time over here. Keep expanding. Keep now this time compressing, stay here, compressing, stay here. So that's why you see these lingerings here. Do you see? Yes? But in the PV diagram, it's almost perfect. So this was another try. Yet another try was this, which is running here. Oh, it's done, I guess. Yeah, it's done. So let me just save this, and it should appear here. Yeah, this is that thing that you saw in the office computer. Now it's here. Brilliant. So this one is a bit different. In this one, I don't go like this and stay here and go like this, stay here. Instead, I run it for Q time steps. I measure entropy, pressure, whatever. Then I start expanding for Q time steps. Then I stop, I measure. While running for Q time steps, I measure. So the other one was like this. Make the process, stop here, make the process stop here, but keep on measuring. Okay, so you get a lot of data, like a lot of jiggling and whatnot. But this time it's just do Q time steps of measuring without any compression or expansion. Then do Q time steps of compression or expansion. Then do Q time steps of measuring. Does it make sense? Let me show you in the code. So I start and immediately I thermalize for Q time steps and measure TSPV. Look, here there is no expansion kind of thing. It's just measuring pressure. As you can see, the walls are not moving. There's zero velocity everywhere. And then once I'm done with those Q time steps, I get to calculate to temperature, entropy, pressure, and volume. One number for all those Q time steps, not Q numbers. Just one number. It's time average. Before it was moving average. Now it's just one time average for Q time steps. Then I carry out the relevant stage of the cycle for another Q time steps. Then the whole thing repeats. So instead of getting all this jiggly stuff, I get a few data, less data, but it's less jiggly, hopefully. And you can see this is the TS diagram, which looks nice. This is PV diagram, which looks nice. I think you have all the information in the world now to do the homework. Because your homework is just this line, nothing else, right? You should just do this line and show that the slope is, in log-log scale, the slope is 2, minus 2. That's your homework. Yes?
Also, sorry. You said about P minus P naught times
Yeah.
P naught.
Yeah.
So, are we supposed to treat particles like individual balls? Or can we take them as point particles?
Well, I meant P0 in a sense that if you want to get a perfect fit, you should think about P0 and V0, okay? But you will get a decent fit with even with this one, probably. But otherwise, it's interesting to see whether P0, V0 will change it or not.
And can we take the gas as an ideal gas?
What?
Can we take the gas as an ideal gas in our homework?
Well, as ideal as it gets. You are doing, of course, this is non-ideal because there are balls.
And collisions.
They are radii and collisions, yes. So, of course, in ideal gas, there are also collisions. There are some assumptions of ideal gas which really don't apply to our system. For example, like the volume that the gas occupies should be nearly zero, which is not the case in our case. Can't be. We don't have 10 to the 23 atom simulation kind of thing. Yeah. Okay. Should we move to the nanoribbons? That will help you with the latest homework. Yes? Who is done with that homework? Who is planning to finish the homework? Many. Okay. So you are interested. Okay. Let me see what I can do. I don't promise much. So back to nanoribbons. Okay, let me take this. Put it here so that we have enough space for everything. So the way that I would do it looks like this. So this is the boundary of the unit cell. And let me put some atoms here. I'm very bad at drawing. And then we repeat this. Do you see the system now? This is the system. Do you have any questions at this point? Any questions at all? No questions, okay.
There's a
Yeah.
question about entropy counts.
Hmm?
There's a question about
Yes, entropy, yes.
Was our calculation about entropy just integration and finding the volume over phase space?
Yes,
Oh, all right.
it corresponds to that. If you think about it deeply, it does correspond to that. And we take the logarithm. Thank you. So the way that I would do it is to number them in the following order: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So far, any questions?
Do we start with 0?
I don't like starting with 0, to be honest, but it's Python code, so no worries, start with 1. Whatever you want to do.
Should it make a difference?
No, absolutely no difference. It's just like, what do you call this?
So we have 14 atoms, but
Yes.
numbers go from 0 to 13.
Yes. Does it bother you? Should we go switch to 1, 2, 3? No? It's fine, right? So let's do the following. Let's add the edges at the end. Like, let's change the edges at the end. Before that, everything is t. Or is it okay with you? So we will construct a matrix, and finally we will add the edges, because it's just 2 lines. You don't need to think about it at the beginning. So everything is t right now. So everything is t. So let me take into account just these bonds. Just these ones. Okay? So how do they look like? They look like this: 0, 1, 4, 5, 8, 9, 12, 13. Goes on like that. And all of these should get a T. Do you see the pattern? There is just 0, 1, then add 4 to both of them, add 4, add 4, add 4, until you run out of atoms. Okay? Do you have any problem? No. This will work for any ribbon, because you can start any ribbon with this numbering and you continue. So none of the e to the IKAs are involved here. Do you have any questions? No. No, right? Yes.
You have already mentioned, first of all, you forget about the edges, but I'm just asking, so 0, 1 and 12, 13 should be DE.
Exactly. But at the end.
At the end.
We'll do it at the end. Okay? Once we are done with this.
One more thing.
Yes.
So is it compulsory, like, to start something like this? Can we start? Like,
Nothing is compulsory.
As you have 2, 3, so can that be my starting point? Like,
Yes. I'm just giving you one way of doing it. Okay? And hopefully this will make sense. We are done with those bonds in purple. Let's move on to these bonds. Oops. Let me put it back. So I will color with purple the bonds that we are done with. Do you see those bonds? They go on as much as needed. So this is one of the terms. Do you have any question? No. So what do we have there? 0, 2, 4, 6, 8, 10, etc. Do you see that it's also t and it goes like 0, 2 and add 4? Are you happy? Yes, good. What else? We have these ones. Right? And they are 1, 3, 5, 7, etc. Remember, Ekin was telling you think in 4. This is what he was trying to say. Like, you figure out a bond, then add 4 to everyone, every index, until you run out of atoms. Okay. What else do we have? We have these bonds that we didn't take into account. They look like this. 2, 4. What were they? 6, 8, 10, 12. These are also T. And then finally 3, 5. Oops. 3, 5, 7, 9, 11, 13. And it goes on. 3, 5. What was the next one?
7, 9, 11, 13.
11, 13. All of this is T as well. Now we have this, the ones with e to the ika, right? So we have 3 to 2, I mean in the matrix 3 to 2 looks like T times e to the ika. Should we go with minus or plus?
Then on the right plus.
It's on the right, so plus, right?
Okay.
It doesn't matter, by the way.
The other one will be minus.
Yes, 3, 2. What is the next one? So we are done with this one. 7, 6. 7, 6. 11, 10. This is this, and 2, 3, 6, 7, 10, 11 are T times e to the minus ika. Okay? So far so good? Are we done with all the bonds? We are done with all the bonds. Now we go to the last bit. The last one is this. 0, 1 should really be TE. That's the only thing that you change, right? And depending on whether you have even number of atomic rows or odd number of atomic rows, it will change. So if you have, let's say, let's count, okay? 1, 2, 3. So when it's odd, it ends with, so 3, 4, 5, 6, 7. When it's odd, it ends with the last 2 also TE. That's it. The last 2 is TE, and you are done, right? So when Na is odd, then the last one is TE, and you are done. When Na is even, right, then you just change this last one, 10, 11 to TE times e to the ika. These ones become TE. The last ones, the last one of those, I'm not making sense, right? Am I making sense? You are, yes, okay. So let me make sense. You did understand the odd case, right? In the even case, In the even case, you don't have this part in the even case. So what you do is, you remember these bonds that we added? You take the last one of them, make it TE. TEE to the IKA. TEE to the IKA. And this one becomes TEE to the minus IKA. For NA is even. That's what you do. NA is number of rows of the atoms, yes. Let me just recover this picture. Do you have any questions? Please ask now, or please ask the assistants. You have a question? Tell me.
As in the example you gave in the lecture for 2 atoms, actually we had 4 in principle, like in the cell, unit cell. So in here, in principle, we should have 28 because it is for 14 atoms.
Say it again. It's not. It is 14 atoms.
It is 14 atoms.
Yes. And A is 7.
And A is 7. But in the lecture, we had that for 2 atoms, that example for 2 atoms.
For 4 atoms.
Also 4 atoms.
4 atoms. It was 4 atoms. Should we go to the example? Four atoms, 4 bands.
That's why this is 4 by 4.
It's 4 by 4.
That means for 14, it should be 14 by 14 matrix.
Exactly.
Not 28 by 28.
No. This is, let me tell you, this is Na equal to 2, which corresponds to 4 atoms, which gives you 4 by 4 matrix. This corresponds to Na equal to 7, which is 14 atoms, which is 14 by 14 matrix.
So,
Okay?
So for 12, Na will be 5.
NA is 12, that means it will be 24.
No, Na is not 12.
When Na is 12, let's say,
Yeah.
number of atoms is 24. It's a 24 by 24 matrix. But you don't need to write every term with your hand. You can just use these correlations, right? You can start 0, 1, 4, 5, etc. until you run out of atoms. So you have 24 atoms. What is the last one? What? What is the last one? 23? Yeah, the last atom is 23. What is the... okay, you don't see where I'm looking. What is the last one of these ones, for example? Yes, it is... No, it's not TE. It's just... I'm asking for the number.
1. It corresponds to 1.
21 to 22. Why?
Because it's like diagonal, but one is shifted.
Look. This is 12, right? So next one is 16 to 17. Next one is 20 to 21. So that's the last one. Does it make sense?
Yeah.
Yes?
Because
Okay.
then it will be 24 to 25 and we don't have it.
Yes. Okay.
This is it, the unit cell for 14 atoms.
This is the unit cell for 14 atoms.
What should be explained in the reports for this?
What should be explained
In the reports.
in the reports?
Or how?
Why are you asking? You are frustrated by the way that your reports...
It's totally fine, but I'm not sure how to write it in the report.
Okay, let's look at homework 3. First of all, you should read the paper. That's part of the homework. I assume that you don't read the paper, because if you do read the paper, you will see, for example, for one of them you should get a really small gap. And that gap should open only if you take into account edges. So for example, in the report you can say that I tried not putting the edge values and the gap indeed closed. For example, once you read this paper, you will see that there are many things to write. But yeah, you can put your bands versus the bands found by DFT, compare them. You can describe all these things that I told you here, like how I take into account each element, etc. I don't know if I'm answering your question or not. Yes? Okay. What else? Hocam, do you have any questions? Are you done with this homework?
Not yet.
This was helpful? Yes. Call it a day? Good. Take good care. Thank you.